Alrighty. So this is now we've got the same formulas more or less, right? In terms of electricity, right? In terms of charge. So instead of potential in this case being energy per unit mass, now we've got energy per unit charge. So this is voltage as in voltage, right? The V is, there it is, right? That's why it's a V. The first one is just the force, right? So if I've got a force and I've got charge one and I've got charge two, and we have the distance separating their centers, and they have to be spheres, right? Or point charges, right? Okay, we can use this formula, right? Now we do have this value of k. This is not Boltzmann's constant. This is a big number, right? So that k is 8.89 times 10 to the ninth, and that's Newton meters squared per Coulomb squared. Okay, so let me make sure I'm not writing the wrong number down there. Okay. Oh, 8.99, sorry, 8.99. I knew it was really close to 8.99 times 10 to the ninth Newton meters squared per Coulomb squared, right? Okay. But just keep in mind that really K is just something we do for high school students because we think they can't understand the permittivity of free space, right? So the epsilon naught, right, is 8.85 times 10 to the minus 12th or something like that, right? But there it is, right? But what's cool about this? What's cool about this is that the force, if we write it down and we substitute this for k, okay, we get q1 q2 over 4 pi epsilon naught, or r squared, epsilon naught, right? Well, if you look at this, that is the area of a sphere. So this is a bit like, remember the brightness formula that we looked at, right? The luminosity divided by 4 pi d squared, right? Okay. This is the same thing going on, right? So the way charges mediate their force, right? The way that they mediate their force, let's say we have another charge out here, right? The way they do that is that they exchange virtual photons. In this case, there's charge carrying particles. This is quantum electrodynamics, okay? And so the farther away we get from this charge, the more area that those virtual photons spread out across. And that's why we've got that 4 pi r squared, right? That at this distance, right, you can imagine a big sphere. Imagine that I could draw a sphere. Okay. Okay. That it's spreading out all of those force carrying particles that are mediating the electromagnetic force, right? They're spreading out over 4 pi r squared. Well, you just didn't need to know that, but that's a cool thing. This is Richard Feynman's Nobel Prize, I believe. Okay. So anyway, that is just our force. This is our field, right? So we've got E is force over charge. By the same token, we've got G is force over mass, right? They go hand in hand, right? Okay. And then, this is fun, right? They don't give us the for some reason they feel like they shouldn't give you this formula. I don't get it. It wasn't in the last data packet. It's not in this one. Don't know why. Okay. So memorize this, right? So you've got G as this one says it's equal here. Let's go back, right? Look, here it is. In terms of G, they've got this guy, right? Okay. How come they don't have it for this? I don't know. I have no idea. They don't like you. They don't love you. They don't love you like I did. All right. So this guy is G m over r squared. This guy is going to be, by the same token, some constant, right? Q over r squared, right? So if we are some distance from a charge, then we can talk about the force per unit charge. Force per unit charge on any charge you hypothetically place there, right? Okay. We can also create electric field by changing the potential over a distance. And I think I showed you this with a sheet of rubber, right? We can visualize this. And most commonly we talk about these, parallel plates. If I had these plates of metal of great in extent and close together, right? Right, we can imagine this, right? Okay, that they are a distance d apart and that there's a potential difference across them, right, of V. We've got some potential. This is, by the way, electrical potential. They need to label that. If they're labeling it here, they should label it there, in my opinion, but that's okay. And so if we look at this, right? This side would be positive, this side would be negative, and we would have an electric field that would go straight down like this, because it's the direction of electric field is what would positive charge do, right? Okay, so the electric field would be from positive to negative, and that's important. Okay, so this is, if we just simply divide the change in voltage by the distance, right? We are going to get the gradient in there. And I think I showed this. We had this sheet of rubber up, right? And I stuck a thing down like this, and I stuck a thing up like this on the sheet of rubber. And in between those whiteboards, we got this very nice flat little pane, a very uniform field. And that's what we do. It's very simple to make uniform electric fields. Near the edges, it's not uniform. Just like on the sheet of rubber, it wasn't uniform. Okay. Now this is potential if you put two charges close together. So let's imagine we have two positive charges, and we can do the same with two negative charges, right? Okay. If I have two positive charges and I bring this charge in from infinity, right? Here it is, very far away, right? And I bring it to some distance r. Okay. This is the energy. This is how much work I would have to do. Now notice that this is positive work. If I bring a positive charge close to a positive charge, they'll repel each other and we'll have positive work. If I let go of them, they'll fly apart. They'll turn that energy into potential, into kinetic energy, right? Okay. So this is positive work. Now, what if one of these charges is negative? Well, these are signed numbers, okay? Signed real numbers. And so if one of those charges is negative, then you would have, of course, negative work, because they would, just like gravity, right? They would want to attract each other. But since gravity is always attractive, gravitational potentials are always negative, okay? In this sense, right? Since charges could be positive or negative, right? The default is that they're both positive, and therefore it's positive work. If they're both negative, negative times negative also gives you positive work, okay? So that's what this guy is, right? This is voltage, right? Voltage is KQ over R, right? So if I've got a charge right here, a big charge. Why is it a capital Q? There's probably a reason. I'm just too stupid to know. Okay. Where's my cursor? There it is. Okay. If we bring it to within R, right, this is the work per unit charge on positive charge. On positive charge is KQ over R. So this guy's Q, right? And this would be the potential. Now, if that's a negative charge, then it would be a negative potential. Okay. And remember, this is voltage. This is the work per unit charge. Oh, that's interesting. Oh, there it is. Here it is. Okay. So here, this is saying that electrical potential is work per unit charge. Okay. They just like to write it like that. That's fine. So remember, work is not just work is not just work. Work is energy. Okay. And then this is the electric field. We're saying that the electric field is negative the gradient, and that's always true, right? If we have a potential, the slope of it is always negative, or the rate at which the rate at which it changes is always negative. So here is the same gravitational formula, right? Here it is in electrical form. Okay, and there you go. That's this stuff.